Welcome everyone. This is the first tutorial in the informal MBT series, and it will be about TLA plus basics. So Dan, please go ahead.
Yeah, so hi everyone. The purpose of this tutorial is to just get like a very basic overview of TLA plus. So how to use the tools and how to structure quite a basic spec, just so that you can get the ideas of using TLA plus and begin modeling things. So hopefully by the end of this tutorial, you should have learned, kind of how to write a spec that checks some basic properties, how to structure your ideas, and especially resources to go to learn more and be able to do more advanced things. So it's like a semi-interactive tutorial. So I was hoping that people will have the tools available on their system. So there is a link here where you can clone my repo, and it has all the jars available. So it has the Apalache jar and the TLA, so the TLC model checker jar, as well as some examples and written materials that you can look through on the second screen if you have one at the same time. And yeah, I strongly recommend developing TLA plus in VS Code with the extension, because it gives you syntax highlighting and a few other features. There's a cheat sheet which you can find here, or it's also in that repo that I just gave you. So yeah, so again, the repo is at Dan WT model checker jars, which will contain the cheat sheet, which you can also find here. Please interrupt me at any time. Tell me if I'm going too slow, too fast, if something's obvious, not obvious, yeah, etc. So what is the TLA plus language? As you probably know, it's for modeling distributed systems and concurrency. And you can think of it as a programming language which doesn't execute against like the CPU, but kind of a model checker executes. And that means that the model checker checks every possible interleaving of concurrent events in the system that you model. So if you model a distributed system, it can check every possible message interleaving. Or if you model multiple threads, then it can check every kind of thread schedule. So it's very expressive language. You can use it to express many things. Yes, there's no real limit, but there are some patterns and common applications. Just some really cool applications that I know of. It's been used in the Linux kernel to check some like lock data structures. It's been used to check like Docker Swarm kit. They're like replicated state machine that they use. And of course, it's used to check consensus algorithms and things in the blockchain space. One idea that I did recently is model a concurrent garbage collector, check it has no leaks. And one example, which there is a written tutorial of, which Igor wrote a model of, is modeling a financial transfers API to check it's not possible to steal money. Spoiler alert, it was possible. So that's hopefully, I don't think we'll get there today to see that example, but I have written a tutorial which is also contained in the repo, which you can look at. So just to summarize, you write a state machine and you write properties that you want to check for that state machine, and the model checker does the work. So you just specify the system and the model checker checks that it's correct for you. Goals of the tutorial. Sorry, I have the Zoom windows like getting in my way. So Alice sends hello world to Bob over an unreliable network. We'll model that system. And we'll use the type checker to help us catch bugs. So you'll learn the structure of a runnable model, how to express the state machine, how to explore system behavior, and how to make sure your models are high quality using a type checker, because like any kind of code, once a model gets to a certain size, it becomes difficult to know that the model itself is doing what you think it's doing. Apalache has support for that. At the end, there'll be a bonus, like hopefully we can just look at the difference between Apalache and TLC for a bit, just to get some, because they're quite different and they have different use cases. So this is a literal hello world example. All TLA like programs, models need a .tla file and a .config file. You write the state machine in the .tla file and you give some parameters to the model checker in the config file. So here we need some boilerplate like module hello world, and we specify the variables of the state machine. So in this case, it would just be a message. And we specify like a set of initial states. So in this case, this one, which is the message is hello world. So it defines, like, initialize this message to hello world. And we define this next, which I'll come back to, but this is kind of like your transition function. So you always define one transition function called next, which defines what transitions between states are allowed in the system. And then finally, check properties of your system. So we have this foo invariant, so we need to check the invariant that always evaluates the true, which clearly will always evaluate the true. And we specify that invariant in the config file, which we can check. So let's get onto a real example. So we'll model a system where Alice sends hello and world messages to Bob in an undetermined order. And there's a network, a non-reliable network that can drop and reorder the messages. If Bob receives hello and then world, he'll become happy. Otherwise, he will just stay in a neutral mood. So this is the entire spec. I really hope it's big enough to see. If not, then the file is available in that repo, which I hope you all cloned by now. But yeah, I'm assuming I'll zoom in too. So the spec, one thing I should say in this tutorial, I'm kind of like prescribing a way to do things. So I'm just giving you, like, I'm saying, do this, do that. But there aren't really any rules, so you don't have to, but I'm just saying, like, common patterns, like a good way to do things. So the good way to structure a spec is to have the boilerplate. So you need hello world at the top and it's kind of like 4 equal signs at the bottom. It's quite weird. Imports called extends in TLA. So we import sequences, which is like a list data structure. And then you should define your state machine and the initialization of it at the top of the spec. So here we have 4 variables and their initialization. The middle region of the spec should be your state machine transitions. So we'll zoom in on that, don't worry. And then at the bottom, you should define invariants and properties that you want to check. So I recommend this kind of like structure, and always use the names init and next as well for the initialization and the transition. And then of course you need the config file. So let's talk about the initialization. So you always write an init operator like this. Operators in TLA plus are defined with 2 equals. So this is kind of like defining an operator. So an operator is like a pure function. And you must define the init for your variables. And the init function should be thought of as a selector. So it's really saying init will evaluate the true in the initial states that are allowed. I wonder if anybody could tell me, maybe who's not familiar with TLA already, which initial states are allowed in the system specified here. It's interactive, guys. Okay, so this init will evaluate the true when all of these clauses are true, because this like sign is the and symbol, so this is a conjunction, and we require Alice's outbox to be the empty set, and the network to be the empty set, Bob's mood to be neutral, and Bob's inbox to be this empty list. So this is the syntax for a list. It's quite esoteric, but that's what it is. So this will hold true in exactly one state, but in general, operators don't have to hold true for one state. They can hold true in many states. And in that case, the model checker will branch and explore multiple states. That's kind of the power of using the model checker. So we should also define transitions. I'll zoom in. So you should, again, in this next operator, list the kinds of transitions. And it's also to be thought of as a selector. So the next says, I allow transitions where I am true. And it next is kind of a pure function over a before state and an after state. So if it's true when that for those before and after states, then it will allow the transition from that before to after state. So could someone maybe tell me when this operator here, this next, will be true, given that the prime syntax refers to the variable in the subsequent state? I really would like to hear an answer for this one.
I guess when x is 0 to begin with, and in the next state it is either 1 or 2. Is this the correct reading?
Yeah, absolutely. So this will allow like 2 transitions, right? Yeah, that's absolutely right. So I hope everyone gets that, because this is kind of, I would say, the key, often tricky point in learning TLA plus is thinking of this next operator in terms of, choosing what's available. It's really more like writing SQL than writing imperative code, because you declare what's allowed, and you don't have to think about how to get there. You just specify this is allowed, this is not allowed.
Wait, so when you have the like 2 types of, I'm not sure how to describe that, 2 operators in a row, what does that mean exactly when you have like the tent followed by, or the other way around?
Yeah, great question. Yeah, thanks for asking. So in TLA plus, the syntax is like using like the mathematical and or, like formal logic and or symbols. And the white space, like critically, is actually like, does matter. So this is, because I'm not using a monospaced font here, it's did get out of whack a bit, but it's like, and x equals 0. So x is unprimed, so this is the original x. And then there's this clause because it's indented. Then there's an or, like disjunction. So so x is 0 in the first state, and in the second state, it's either 1 or 2. Yeah, thanks for asking. Yeah, so again, I would say it's,
regarding
please.
the previous one, this next operator will allow only one transition, right? It cannot be repeated, right?
Yeah, absolutely. So this is where the kind of the magic comes in, because the model checker will check all of them. So if this is possible, the model checker will check your system where like every transition is taken, right? So it will check, in this case, the system where x went from 0 to 1, and it will check the system when x went from 0 to 2. And then, so you can imagine if it went to 1 and then somewhere later it crashed your system, then you would be able to find the problem. So yeah, I guess that's quite important. Yeah, did that make sense?
Yeah, thank you.
And again, I'm prescribing advice here. Try to think when you write your transitions in terms of verbs and actions in your system rather than state. So you should write actions like this message gets sent, or this transaction occurs, or Bob becomes happy, or Bob checks his inbox. Feels kind of abstract, but yeah, just try to say like what human, like not human, but what kind of like concrete things happen in your system. So I would say what makes it easier is like this often maps directly to like API calls, for example, because those are actions, right? Yeah, so coming back again. So the next, because it's a disjunction in itself, it will hold true if any transition in any of these like sub operators or sub actions are true. So yeah, if any of these are true, it will pick 1, or rather the model checker will actually check all of the possible branches. So we can zoom in a bit here. So let's look at this Alice send operator, and it will be true if M not in Alice's outbox. So again, this is kind of using, the syntax is quite strange, but it uses this like backslash and then a keyword often instead of like a symbol. So M is not in Alice's outbox. And also the outbox in the next state, so it's got this prime variable, contains M because it's the union of the previous outbox with M. And similarly for the networks, the network in the next state contains M and nothing else changes. So you should always specify like the before and after for every single variable. So if you have some that are kind of irrelevant for the action or the verb, then you can write them in this unchanged list. So in this operator, Alice sends a message. Bob doesn't do anything, right? So he's unchanged. So you write Bob's mood and Bob's inbox are unchanged. And the network loss will be true if there exists an element in the network currently such that the network in the next state is equal to the network in the current state without that element. So can anybody tell me like what kind of, well, I mean, it's kind of obvious, I guess it's in the name, but this is like a network loss, right? So it's a message has just randomly been lost because a message was in the network before and in the next state it won't be, and nothing else changes. The network deliver operator is true if there's an element of the network such that, again, this is going back to the mathematical symbols thing, this \E is like there exists, right? So there exists element in the network such that Bob's inbox will then contain like this element appended. So again, excuse the bizarre syntax, but it's like \O to like concatenate sequences. So as we had Bob's inbox as like a list, then we append like the one element list with that element, so that Bob's inbox in the next state will have that element at the end. And the network will also lose the element because, you know, once it's delivered, it's delivered. And again, we have the unchanged. And Bob will check his inbox. This is possible. And we say we can use like if else statements here. Bob's mood dash. If Bob's inbox currently is hello world, then he becomes happy. His mood becomes happy in the next state, else he stays neutral. So can anybody tell me when this action is available? Is there any condition on Bob's mood in the current state or any condition on Bob's inbox in the current state?
Only if Alice sends hello world in this order. I guess
Right,
the sequence keeps the order. I guess it's not just the set.
Yeah, so almost. So there's actually, this action could be taken at any time without condition on Bob's inbox, because it's like if Bob's inbox is equal to this, then his mood will become happy as neutral. So it's like because of the else, it like matches every possibility for Bob's inbox. So actually Bob can check his inbox at any time. Yeah. So long as these other things are unchanged. Okay, so yeah, that's it for this simple state machine. Hope it made sense. And now we can kind of check some invariants and properties. So you check properties by specifying operators, where you define some like logical condition over the state, and then you provide that operator to the model checker. So for example, here we have nothing unexpected in network is the operator that says for all elements in the network, that element is also in Alice's outbox. So it's saying, so by the way, this syntax is for all, like /A. It's saying kind of what it says, nothing unexpected in the network. You know, if something is in the network, then Alice must have sent it. We don't want it to appear by accident. I would say it's quite easy to see that this is true from the state transitions that we defined. So like I said, it's a simple example. And I would say a more interesting one is this not Bob is happy. So this is an operator that makes use of the let keyword, which allows you to define more operators kind of inline and use them locally. So not Bob is happy is defined as this in which is using this tilde for logical negation, like immersion. So it's like tilde Bob is happy, and the tilde is not, so it's not Bob is happy. But we define Bob is happy as Bob's mood equals happy. And we can provide this to the model checker.
Sorry, Daniel, one clarification question. The let construct here, is it just for illustration? I guess, is it not, is it necessary?
So
Would you be able to just write tilde and then brackets and Bob's mood equal happy or something like that?
absolutely, yeah. It's just for illustration because it becomes quite like it's a very commonly used thing, like as you write bigger specs. Yeah. Thanks for the question.
Short question about the previous slide.
Yes.
When you're saying about Bob check inbox, when can happen, you're saying that can happen at any point because of the else. That means that the model checker could try to model a sequence, infinite sequence of
Yeah.
Bob check inbox.
Yeah. Yeah.
So that's not necessarily the best way to go about it if you don't
Yeah.
want the model checker.
Yeah. So you should specify fairness conditions.
Okay.
I'm kind of, yeah, you're absolutely right, Marius. I'm trying to, just keep this as a basic tutorial, but you're totally right. You need to definitely take into account things like this, like infinite loops and, you know, allowing the same action repeatedly that doesn't change anything. Yeah, thanks for the question.
Just one more small question here. So I understand that the double equal means definition and the equal means you are checking a state, right?
Yes.
Okay, thanks.
Yeah, so it's equal for comparison. Yeah. I would say like some of the quirks of the language are it does take into account like precedence quite intuitively, but sometimes it can be, I mean, yeah, like it usually you don't need to put parentheses around things, but sometimes you do. So. Okay, so yeah, we have these two simple invariants for this system. And of course, we should specify the invariant in the config. And we should then run the model checker. So I've got two separate commands here. TLC, if you've got an alias for it, or the entire Java command. I don't, yeah. So I'm not sure if you guys in the background have been getting the tools set up, but maybe we can check together what happens. I have it here. Not Bob is happy, and I can check with TLC TLA.
Then I think we see only your slides, not nothing else.
Okay, I would just reshare with the correct screen. So, okay, hopefully you can see my terminal now. So we can check this one, or we can also check this one too. So yeah, like, has anybody like managed to check this like in the background while I've been fiddling around?
It works.
Great. Okay, so maybe we can just digest the output a bit together. So yeah, we ran TLC of hello world, and it will automatically pick up the config because the config was also named hello world. Otherwise, you can specify like a config file specifically. And yeah, unfortunately, the model checker gives you output in this like extremely hard to parse form. But yeah, we can just go ahead and read it anyway. So what happened? It computes the initial states, which we had one of in this example. So one distinct state generated. And it tells us immediately, okay, I found a violation of not Bob is happy. So if there's a violation of not Bob is happy, then it means at some point Bob is happy, right? So that's by using negation, we can kind of find behaviors which we intend to be there. So we want a situation where Bob is happy. So by checking the invariant not Bob is happy, if it finds a violation, Bob is happy. So scrolling down already, we can see in the final state, state 6, Bob's zoom is in the way. Bob is happy. So we can try and see what happens. There's the initial state. The network's empty, the outbox is empty, Bob's inbox is empty, and Bob's mood is neutral. Alice sends hello, and it goes into her outbox and into the network. And she also sends world. And then hello gets delivered from the network into Bob's inbox. And then the same with world. And then finally, Bob checks his inbox and he becomes happy. So straightforward stuff. TLC will also tell you the number of states generated and the total number of distinct states generated. So the way TLC works is it's like a breadth first search exploration of all the states starting from the initial state and taking all these branches as allowed by your next operator. And what it does is it hashes the states so that when it takes a state off the queue, it takes the hash of the state and then it checks if it's already seen that hash. So the number of states generated is the total number that it pulled off the queue, or rather pushed onto the queue, probably. Whereas 18 is the number of distinct state hashes it found. So that's the total number of states in this system, which probably in this case you could like work out quite easily just on your fingers, because you have like 3 possibilities for the network, right? Or 4 possibilities. You have the empty network, hello world, or just world. And then you can kind of take a multiplication based on the number of states of each variable. So this is kind of how to interpret these states. And the depth of the complete state graph search is 6, because it took 6. There were 6 states in the sequence that reached this conclusion. So you may notice that I needed to like kind of work back which action was taken by looking at the states, right? So the output is states rather than actions. So it doesn't tell you how it got from one state to the other. So in the general case, it's possible to get from one state to the next in like by taking multiple actions in your state machine, which can get confusing. So I recommend in a real model, like you can use you could add like another variable saying like action taken, and then in each, so you would do like and equals and then you would do like you would specify like Alice send something, because this helps you kind of actually figure out like which transitions were taken. Right. Cool. So maybe how would you check nothing's unexpected in the network? You would just change this line, right? You would just change the line in the hello world.com thing. Cool, so that's it for the Alice and Bob model, like without types. And now I'll show types. But first, I should probably ask, is there any questions? Okay. So yeah, you can imagine that as you write more and more complicated models and use more constructs from TLA+, it's difficult to know that the model itself is actually doing what you think it does, because the model is essentially code, right? And all code, you know, you can imagine that you can introduce an error like every 10 lines that you write on average. So for sure, when you write a large model, it's initially going to do something weird. And type checking is one tool that you can use to get towards a model that's actually doing what you think it does. So TLC does not have a type checker, but Apalache does. So we will go back and type check this hello world example. And luckily, because it was such a simple spec, there's not many type annotations that we have to write. Apalache can actually just figure out most of them. And if it needs more annotations, it will tell you. So yeah, like really simple. Alice's outbox is a set, right? So we must write this comment because all Apalache annotations are inside comments, TLA comments, which are like \***. And then we write add type set of string. So Alice's outbox is set of string. Same with the network. Bob's mood is just the string. And Bob's inbox is a sequence of string. So sec. So there's some shorthands for these, which appear in the docs. We should probably also specify the type of operators. So we specify the type of Alice send as a function. So the function, function's the wrong language. It means something else in TLA, but really an operator, taking a string to a bool, because it takes a parameter in, which is a string, and it evaluates true or false. Really, there are hidden inputs, right, which are the totals, like the big set of variables and the big set of primed variables, so variables in the next state, but you don't need to write them in the annotation. So yeah, maybe we can check this one. Okay, running Snowcat type checker, the types are great. All expressions are typed. Excellent. Yeah, so strong recommend to use the type checker. It will, coming back to a question that Ivan asked earlier, when you have these, this let, it can be the case as you write more advanced TLA specs that you will use a lot of these like inline operator definitions because you can kind of think of them as like temporary variables that you can use in your computation. And it can often be the case that this is where Apalache is going to ask you to write an extra annotation because its type inference will only get so far before it has like an ambiguity that it can't resolve. So you'll need to annotate here, like you would probably write like you would just write like on the line above like this. Another one like this. Cool. So yeah, to be honest, like I was not very sure how long this would all take. It was actually fairly quick. So maybe I can shed some light on the difference between Apalache and TLC. So I have some basic notes here. I'll switch to a different set of notes in a second. So Apalache and TLC are just completely different types of model checkers that use different algorithms. They both do the same job of taking your TLA spec and converting it into like their own representation, which they can then check properties of. Apalache does it by, it kind of expands all the logical statements into a formula, which it checks with like an SMT solver. So it uses the Z3 SMT solver, and it means that it represents every variable symbolically, and then it solves like mathematical constraints. So for example, if it becomes quite hard to reason about because the formula that it solves will look nothing like the formula that you write. But you can imagine that the formula that it actually solves contains many of these constraints. For example, if you had a variable x and there was some kind of transition where it had to be positive and less than 42, Apalache can like very easily find a concrete example of X where this will be true, and it will allow the transition to happen. Oh, sorry, I've been completely ignoring the chat. Sorry. So yeah, feel free to like jump in with voice, guys. It sounds like Andre has answered this. Okay, great. Yeah, so sorry about that. Yeah, so coming back to the discussion of the model checkers. So Apalache is a symbolic model checker, and it'll be able to provide you like concrete values for these like tough constraint problems. Whereas TLC just literally computes every state like in a more like concrete way. So that means TLC will compute like one example where X is 1, and then it will compute another example where X is 2, blah, 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 up to 42, and they will all go in the queue. And that's going to be expensive, right? Because you know, there's no semantic difference because your model doesn't care if it's 1 or 41. But TLC is still going to have to check all of them. So this is kind of like a fundamental difference in the algorithm. And also because Apalache solves this formula, the formula should be bounded in length, and it's bounded in a way that matches the number of steps forward that your system takes from the initial state. So you define an initial state and these transitions, and Apalache will probably only be able to get, you know, a certain distance from that initial state. So it'll take like, let's say, a dozen actions, and then it usually becomes like intractable to get further than that because the formula they would need to solve becomes too big. That's my understanding anyway.
Sorry, Daniel, I did not understand how many steps is realistic for Apalache?
So in my experience, like I'm sure Igor and Yuri are going to jump in, but in my experience, like around like 6 to 12. Yeah.
Yeah, thanks.
I mean, it really depends, but yes, it's when you have 10 steps, it starts to slow down because basically the solver has to pick between different actions and, you know, just have an exponential blow up in the number of combinations.
Yeah. So there are like different problems which are suited to different model checkers, that's for sure. Yeah, so like a great example actually is one which I could come to if like this time, which is this Ethereum model that Igor wrote recently, where it's modeling like a financial transaction API, which uses like integers. Thanks, man. Yeah, so it uses integers, and it's modeling an API that uses integers, right? So it finds an exploit, and the exploit it's unlikely that it's going to require like 100 API calls. In fact, it only requires like 8 or 9. And because it uses integers and it's got this like it's like a nice length of nice number of transitions, like around 8 or 9. This is like perfect for Apalache. Whereas there's problems which TLC would be more suited for. One example I can think of is like I was modeling like a current tree data structure, which was kind of like modeling some multi-threaded code, like quite, so the TLA model mimicked the code very closely. And you can imagine that, you know, data structure algorithms, they take many more than 12 steps. You know, to find the bug in that system, I needed like 100 steps. And in that case, TLC was, you know, the right choice there. Don't forget, you can type check with Apalache and then run with TLC. There's nothing stopping you taking the best features from both programs. Yeah, wondering if I have more to say here. You can. Yeah, so there are additional features which I would say come under like a more advanced category that Apalache has, which are really cool, which TLC doesn't have, which are, it lets you check trace invariants. So instead of checking an invariant over a single state like we have, so we checked Bob's mood in every state, right? Apalache lets you check invariants or behaviors of a trace is. So it will give you the entire history of the execution. So that kind of lets you, it's less restrictive. You can check more interesting things.
Could you give an example just to understand if I got it?
Absolutely, yeah. So let's jump ahead a bit to. Okay, try and get this all on one screen. Yeah, so this is actually a invariant from the Ethereum exploit model that Igor wrote, and he wants to check that in the API that for any like transfer, the approval was given in the past. So there may be a transfer that takes place like between two states, and because you need to check that it was approved in the past, then it would be difficult to check by looking at one state. It would be possible, like, you know, if you just included the history of the system in the state, that's like a trivial workaround. But the problem with that is it just like adds more state. So I would definitely not do that in TLC. In Apalache, it may be less problematic. And actually, I'm not sure, maybe Igor can say that's, I guess, how this is implemented under the hood. Like, I'm not sure where the input for this comes from, but like it has essentially the solution.
What's the problem?
So I think I was just going a bit like on a tangent, but essentially we were like discussing the difference between trace invariants and regular like state invariants. And yeah, I think the case is quite clear here because Apalache solves the formula for like every single state, then it kind of has this trace for free. Whereas TLC, on the other hand, would not, you wouldn't be able to check this because you would have to kind of collect each state in a history variable by yourself. Does that make sense, Ivan?
I mean, it's not okay. So in TLC, there is an operator which is called trace in TLC model, right?
Yeah, but I've heard that this is like not not usable. Like it's like
it's not very efficient. I guess it has to go and I'm not sure exactly how it's working. I guess it has to go over the stack and collect all the states on the stack.
Yeah, I heard it's like quadratic in the number of states. So like I would say,
yeah.
Quite
in Apalache, just you write down a formula that we have the states symbolically, right? Basically, you know which constraints each state corresponds to, and you can just give this, you know, symbolic versions of the states, and you can reuse them in the constraints here.
Yeah, that's right. So yeah, I hope that answers that even. But maybe we can go through this example together, because now that we've seen like kind of the basics, I hope that everything I said was understandable for everyone so far. And like now might be a good time to actually explain this, as Ivan asked about, because it's using some more like, this is kind of like a real example, right? So you don't want to see hello world, you want to see something real. So maybe we can go through this operator together. So the operator is saying all fund transfers have sufficient approval, and the trace is, as the type here says, is a sequence of state. A state is an alias, like a type alias for like basically like all your state variables grouped together. And we can see like, what is it saying? So for all spender and from address in the addresses, so it's picking every possible pair of addresses, spender and from address in addresses. This other clause will hold, right? And then it's using this these few like let operators to define some like inline values or inline operators, which can be reused later in the computation. And then finally, like the kind of what this ultimately evaluates to is just like this last line here. So the sum of transfers made should be not positive, or it's positive and there exists an approval for those transfers in the past. And yeah, so these are using things that we defined before. So we defined this sum of transfers here and the exists approval in the past here. Probably to give some context on this, I should just explain like the system that was being modeled a bit. So there's an Ethereum API for token transfers, I believe. I'm not really into Ethereum, so probably I'll say something wrong, but it's possible in Ethereum for an account to delegate the ability to spend its funds to another account. And it does that by, it sends like approval transactions into the pool, into the transaction pool. So it says, okay, if for my address, I will allow this other address to spend this many funds in total. And those transactions get submitted to the pool. And when they're executed in future, like once they're executed, the account who was given the ability to spend funds can then just, as it likes, spend funds from that other account up to that sum value. So here there's like this spender, which is the person who was given the ability to spend, and the from address, which is like the address that who's like points at spending. So we want to check that this holds for every possible pair, where addresses, we just specified a okay. Yeah, so addresses, we just hard coded like 3 addresses. Yeah, 3 is like the minimal case for this system, right? Because you need one guy to spend another guy's coins into another guy's purse. Yeah, so we take all possibilities of 2 addresses from those addresses, and you'll note that like these can be the same, right? There's nothing saying that these cannot be the same, except for, yeah, I mean, yeah. So yeah, maybe we should break down these like sub operators which are used. But so far, does everyone understand like the broad structure? So like the property that's being checked, right, is like, is that clear? So it's saying like the case that would make this fail is that there was a positive sum of transfers without approval. So maybe that's an easier way to think about it. So you want to check that there's nothing that will make it fail. And yeah, so this is where we jump into some like real like TLA, how it really looks. So we can define this sub operator transfer indices, and it's a set because it uses the set syntax. And the set is made of all the indexes in the domain trace. So domain is like it's like the mathematical domain of a function. So because trace is a sequence, in this case, the domain of the trace is like all the indexes. So if the trace is like 8 steps long, then the domain will be like the numbers 1 to 8. So this is like the indexes of the trace. And then with the colon, it's like saying such that. So there's an index. So it's the set of all indexes of the trace sequence such that, and then it uses yet another let, which defines this temporary, which says that this tx, like temporary variable, let's say, is the last transaction made in the trace element I, so in that state. And we want the transaction, so tx for transaction, the tag to be transfer from, which is saying like, you know, I transfer funds from here to here. And the transaction did not fail, so it went through. And the from address is this address up here, which was selected. And the spender is this one. And the transaction value is positive. So it's like all the indexes of the trace, so all the states where there was a positive funds transfer. And then we use this in keyword to be able to use this in the future. So now we can reuse this here. So we define this sum of transfers, and this is where like you have to take a leap, hopefully feeling good about recursion and so on. So it uses this fold set operator, which is built into Apalache, which is like a convenient like way to process sets. So the fold set is like I guess it's like there's similar things in most languages nowadays. I just don't know if they use the word fold, where you like repeatedly apply a function to the next element of like a generator, and you accumulate the result, like the successive result. So it's like you fold the set transfer indices with this adder, starting from value 0. So it will take an indices from this transfer indices set where there was a positive transfer, and it will apply this to like the value you have so far. So you have the sum, and then it will take the the value of the last transaction, add it to the sum, and because this starts with 0, the result is like the sum of transfers. So I think that's straightforward.
I guess it's the hardest thing actually. The whole TLA.
Yes.
Or the sum ups and apply things to sets and sequences.
Yeah. It's one of those things you kind of get used to, I guess. So now we have this sum of transfers defined in this temporary variable kind of, and we can use it again. Actually, we use it down here. Oh, and here. So we should define one more temporary variable, which is we want to is a Boolean. There exists approval for the sum in the past. So again, we iterate. We like it's not iterate, but like we search over the indexes of the trace of the execution, and we define the transaction that was an approval. So as like this last transaction. So we check that the tag is approved, and the sender was the so the spender that was approved by this approval transaction is now this spender, and the from address and the approval transaction was sent. So the sender was sent by the address that's now having funds transferred away from it. And crucially here, we want to check that all transfers are made after the approval. So it's no good if someone can transfer your funds before you approve them, right? So yeah, so we check for all j, so for all j indexes in this transfer indices, I is less than j, so the index of the approval precedes the index of the transfer. The approval did not fail. And finally, the total approval should not be less than the sum of funds transferred. And then once we have this Boolean, we can use it here. So yeah, reduce, that's right, sorry. Yeah, so I hope, Ivan, was that like an understandable real life example of this trace invariant feature?
Yes, it was.
Right. Yeah, maybe we can go ahead and check that. So now time to use Apalache. With Apalache, it will assume you want to use like init and next, so you don't have to write them in this config file, right? So yeah, Apalache will kind of take care of that for you. And also you can specify an invariant on the command line with Apalache. So actually we don't need the configure for using Apalache. So here's the actual spec in f.tla. All fund transfers have sufficient approval. And we can check see what happens. Yeah, so this is related to what Igor was saying earlier. Like you can already notice as the state gets further away from the 0 state, it's kind of checking a longer formula, and it's taking longer to kind of get to the next one.
Is there any caching of computation if you've done, like if you say created one large run in the past and then you add a new state, can you cache the old set of calculations and then just add the new state, or does it recalculate everything each time?
Well, it doesn't calculate any states. It actually solves constraints, right? I mean, yeah, I don't know any solver that actually could, you know, cache constraints. I'm not sure. And some theorem provers can do that, but solvers usually wouldn't cache intermediate constraints. I mean, it's a good idea, but I don't think it happens anyway.
Yeah. If you were using TLC, I guess there could be something like where you can
Yes,
somehow,
TLC can actually,
Yeah.
you can stop TLC and say continue from there, you know.
but I don't think anyone
copy-
uses this because it's like
No.
if you like got to a state, if you reached a state and then paused it and then changed your model so that, and you accidentally made the state unreachable and then you continue checking, there would be a possibility that it would continue checking from like an unreachable state and just give you nonsense without you noticing. So it's like becomes quite hard to reason about actually for real cases. In practice, like you just restart model checking every time you make a change. Okay, so yeah, we can break down the kind of the output, and Apalache has like multi-passes. So the SANI, it will pass your TLA and it will check your types, so that's all good. Check the config. So this is okay because we gave our command line options. Yeah, I'm not like sure on all these are kind of like the internal passes. So desugar, unroll, etc. And then the bounded checker, so that's the most important part. So it will start checking a formula with like 0 states, and then it found everything was okay in that formula. Then it'll check one with 1, and then 2, 3, etc. And when it got to 8, it found actually there was a problem. So there was a violation of this. All fund transfers have sufficient approval. And it will give us kind of like an output counterexample. So counterexample 1.tla. And in theory, the output is like similar to the one that TLC gives you. Yes. So this is the counterexample, meaning the counterexample is the trace that violated the invariant, right? So we can see that you got to state A, and then once it had reached this, the total sequence violated this. So to be honest, it's like kind of a mouthful to digest the TLA sometimes, especially if you're not familiar, like because the syntax is just quite bizarre. Maybe for the purpose of this tutorial, I can summarize, but so it gives you the variables of our structure in each state, right? And in this case, we had balance of variable. So this is the balance of the address. So it's the address to int. So it's an address function. It's a function mapping addresses to integers, so addresses to their balance. And we had the allowance, which is a function mapping tuples of 2 addresses to the allowance given. So from the owner is the first element, so this address, and the spender is the second element. So that's kind of the mess you see here is this allowance, because yeah, like there's just a curiosity that sometimes like the internal representation will use this function concatenation. So it's saying like this is a function mapping address 1 to 0, and then it's like merged with this function mapping address 2 and address 1 to 0, and then yeah, there's like this nested merging, which is like, yeah, it's just like one of the quirks that like comes with this kind of stuff. So don't be put off by that. It's actually quite understandable once you get used to it. And of course, you know, we're building tools currently, like which will help you like convert this to JSON and stuff like that.
Does Apalache attempt to simplify the found counterexamples?
So it will, because it checks like successively longer sequences, you always know that your counterexample is going to be minimal in the number of states in the trace. But I'm not sure how much it simplifies with respect to like parameters, like integers. Like if it's going to give you like a huge integer, when like,
I mean, the solver would just spit out whatever it finds. And usually it's quite lazy. It wouldn't try strange things first. It would try zeros, empty sets, you know, in some sense. But yeah, there is no minimization, as you probably know from property-based testing. That's part of the problem.
yeah, TLC will minimize for you, though, like, because
I mean, TLC wouldn't minimize. It would try to find a shorter counterexample, but it wouldn't find, you know, the smallest counterexample in terms of the size of the set, for instance. And in property-based testing, you can do it. It will try to reduce.
Yeah, that's true. Yeah, because TLC, it doesn't like check this successively longer formula, right? It just pulls off a queue. So if it just happened to evaluate and push things onto the queue in an order that resulted in a long, so say it pulled a state off the queue, the processing queue, and then it found this state breaks an invariant, it would not, like, I'm not sure how it works actually internally, but it would not just like give you the trace so far up to that state. It would actually like recompute, I think. I'm not sure how it works internally actually to minimize. Maybe, do you know, Hugo?
I mean, TLC is doing breadth first search, so it should also give you the shortest counterexample in principle. But it does it in parallel, so sometimes it gives a longer counterexample. It doesn't minimizes after that.
It does do some like minimization, I believe.
Okay.
Yeah. But yeah, I'm not sure. I'll have to look into it. Yeah. So yeah, simplification is kind of limited, but it's normally not too bad, to be honest. So yeah, like I'm not sure how much it's worth to kind of go through this, because it's probably tricky to understand anyway without like the full context of the spec. But yeah, that's how we can run Apalache for a real example. Yes. Yeah, so really that's everything that I have prepared for this tutorial. I really hope it was informative. There is
question. So can the test just now also be run on TLC, or is it like only available in Apalache?
Yeah, so this checking these kind of trace invariants is like an Apalache only feature. In this,
I mean, it wouldn't be easy to check the specification as TLC, or maybe this one. I mean, one problem that here, for instance, we're using integers, and we even don't restrict what kind of integers this, right?
Yeah, that's true.
Yeah, in this example, we could probably define a small set of integers and run CLC. But we have examples, for instance, where we produce overflows in Ethereum, right? And there you would need 2 to 256 bits, which is quite large, and TLC would never even go there, right? Again, you will have to carefully craft the set of integers for TLC. You probably can do it a bit like property-based testing does. You just define a set of things on the edge and other things, and try exploring them as TLC. But by default, TLC would just not do anything here. You have natural numbers.
Yeah. Yeah, that's true.
In terms of syntax, can you define, like most of what we're looking at has the operators defined within an operator directly. Can you define like helper operators? Like if you want to check the same thing multiple times?
Yeah, of course. So not every operator needs to be like an action or an invariant. You can just define like, yeah, so the addresses is actually, we use it as a constant, but it's essentially like a helper operator, but you can also do like my helper add a speed, just, yeah, whatever you want. Yeah.
I mean, that's in scope for everything that's in the, I guess, checker, or for everything that's in scope for this model.
Yeah, yeah. Yep. Yeah.
Regarding the let operator, and mostly to understand how is a good practice to write spec for TLA spec for complex projects. So of course, for the hello world, you don't really need a let operator. Is it okay to understand from the invariant that you showed us before from the Ethereum example, that it's good to kind of start backwards, to go about backwards, to say, okay, look, this is what we want, and we have some black boxes, which is sum of transfers and existing approval for some in past, and then go backwards and kind of build them backwards. Is that a good approach to build such complex invariants or operators in general?
Yeah, I think that works. I think it's kind of like when you're just doing regular programming, like you realize like, oh, I need this like data, I need this data, and they don't depend on each other, so I can just, move them into functions, and yeah, it's quite similar to that, I think. So
Thank you.
I think it's quite similar to just like regular programming.
So when you're running these, when you're checking these, does this kind of get expanded like they were macros or something, or is it a way to understand it?
Exactly. They're actually kind of macros, unless you have recursive operators which trigger, right? I mean, Apalache cannot even, it has some limited support for recursive operators, but we are going to deprecate it and just remove it because it's much easier to handle fault operators like fault set, fault sequence. They have an upper bound on the length of the input. And recursive operators in TLA, you even don't know whether they terminate or not. So unless you have a recursive operator, it's all easy. It's like a macro, exactly as you said.
Okay, and one unrelated question that is coming from before, but I didn't want to break the the cadence. When you have strings, so how are usually? I mean, I have no experience. So I'm just hoping for some experience report, like this length of strings. Like, do you usually limit them, or is it a source of like a state explosion? I mean,
No. So this length of the string won't matter at all because this like the state explosion will come when you have like multiple states. But so like if you have a variable that's a string that can take like there's this like, so if you have a variable that's of type string and there's states in your system, like 1,000 different states with 1,000 different lengths, like 1,000 different strings, then that will cause a blow up. But like having like a long string in of itself is not, does not affect it at all. Like,
so strings actually, at least in Apalache, they're treated as constants. You can think of a string just as a fancy identifier. And that's what they actually are in TLA+. Until recently, TLC also treated strings like that. Then somebody complained and they decided to make strings. Like strings, like sequences of characters. And actually, nobody is using this feature except maybe a couple of people. I don't know. Because in TLA, you want to reason about values. You don't. If you want to do string manipulations, you have to define sequences of characters, and it's up to you what it means to be a character actually. Because they can be ASCII character, they can be UTF characters, whatever, right?
So basically, in your experience, you don't feel the need of manipulating strings themselves.
No, I would just remove the strings at all if I was designing the language. They're just used as identifiers.
Yeah, you can just use integers for everything.
Yeah, integers. I mean, here you really have a difference between Apalache and TLC.
Yeah.
Because for Apalache, integers mean it has to reason about integers, and integers usually make things much harder for the solver because it has to solve linear constraints or some constraints of integers, right? If you actually, that's like a general advice. If you can replace your integers with strings, do that. It will be much more efficient right away. Just really. Whenever you have integers, you replace them with strings, you'll get the speed up immediately. Just a general piece of advice here.
Yeah, for Apalache, I think in TLC, integers are just will be faster though. Like,
I mean, in TLC, it's maybe the opposite, but I mean,
yeah,
TLC
I think so.
Also hashes, the strings and produces an integer, I guess. I'm not sure actually. I'm not sure how it internally handles them.
Yeah.
Using strings instead of integers with Apalache gives a speed up, even if you don't introduce any arithmetic constraints.
I mean, if you just use integers as constants, maybe it's not so bad. It depends on the solver, right? But if you just use strings, for sure they're going to be constants, and there is nothing, complicated about constants.
Yeah.
I guess a smart solver as Z3 may discover that these are just integer constants and literals, right?
I guess if you just have equality between integers, maybe you won't kick off the whole linear arithmetic.
I'm not sure. I don't know. It's like a matter of experimentation. Yeah?
Okay, thanks.
I would say there's one feature in TLC where you can define like symmetries in your system. So you can write functions like symmetry functions, which can make two states like hash to the same thing, kinda. And so you could, if you don't care about like the order of integers, for example, then you can define a symmetry so that that order doesn't matter. And if you use integers, TLC will be able to swap the order faster because it just like its data structures that it uses for integers will just be more efficient, I believe. So that's like one instance where you can benefit from using integers in TLC over strings. So it's kind of like opposites. Yeah, it's interesting.
I mean, you can also use these model values in TLC. There is like a hack that introduces special values for, I don't know how to call them. The strings also have this problem that they can be mixed together, right? If you have strings and you use them for different values, for different variables, you don't know that it's never possible to use that string for that variable, right? And model values are also a refinement of this idea that you can say these are values for this specific type. So that would be similar to constants as we discussed here.
I have a question on the model, not the on the programming model here. So can you only be in one state at a time? Like if two states are legal, given the constraints that you've defined, and then both of them specify a transition, you can only do one of those transitions at a time. Is that correct?
Yes, but you can do one, like, you can just imagine that the model checker will take care of checking both of them at some point for you. I think like a related point is that you should, it's good practice to make sure you're like, your actions are disjoint. So like, I mean, in the sense that this is kind of like why you account for everything in each one, like you include every variable in each action. Yeah, so that you're not like using partial logic from each one. Like it's kind of, for example, like they both, like these three share unchanged Bob's mood. So you could pull that like bit of logic out somewhere else, but just as a best, like a simple guideline, like just try to account for each variable in each action. That helps you kind of like mentally divide things and make sure you think of things in terms of like verbs.
Yeah, I'm thinking of a case of like a timeout, for example. If you want to be like timeout, like fire a timeout, now the timeout has fired, but also a different state might be legal. So the way you would model that would be like, and timeout has not fired or something like that to make sure that you don't accidentally make it possible to enter that. Yeah.
I see. Yeah.
But I mean, usually timeouts are modeled as non-deterministic choice. So you just say, look, I don't care when it happens, it just happens, it can happen, right? And when yeah. So if you handle the timeout, yes, you have to save somewhere that you have handled the timeout. Otherwise, you can probably get it again if you evaluate the transitions in the next state. Yeah. I mean, it's not doing a lot of things for you. Just if you know that A or B are possible. If A has happened, there is no guarantee that A will never happen again. That's basically, yeah.
Regarding type checking, I didn't understand exactly why it's necessary. And the question is, can you actually modify the type of a variable within an operator in TLA+? So for example, Bob's mode here initially was a sequence. Can I make it something else here?
So Apalache won't let you do it, but
TLA will let me?
TLC maybe will let you. Yeah, I think it will let you, but you just have to be careful. Like, so if you have like, if you also added like Alice's mood later, and both of them changed type, so you had Bob's mood and Alice's mood, and like both of them could be sequences or strings, then if you ever compared them, then they need to compare as the same type. That's the only restriction.
Okay.
Yeah. Otherwise, it will just crash.
Small question. Seeing the unchanged, is there a syntactic way of maybe saying unchanged everything I haven't mentioned in this?
No.
Okay.
No.
Because that would prevent a lot of mistakes.
Yes.
That's a very often asked question. It's like everybody wants it.
The other thing to watch out for is like doing like so you write your action and then you do like and x dash equals 42, and like just by accident, because it's, if you're writing a long action or something, this will never fire because it's impossible. And it's already 42. So, well, more strictly, be something like this. It will never fire, but it's very easy to miss this in your code. So that is something to watch out for.
There is the convention that sometimes people will assign like a sequence of variables to a variable itself, and then you can just say unchanged that variable which stands for the sequence. So if you have like sets of variables which don't change together, you can sort of give an alias for that set of variables for the unchanged.
Right.
It doesn't solve the problem really that you're describing. But.
Yeah, like you could just do, replace this one by Bob stuff.
Yeah, exactly.
Yeah. So feel free to ask more questions. I was thinking maybe just as a last thing, I can just talk a bit about the ecosystem. I think it's like quite useful knowledge, just to get an idea of like what tools are available. So we already talked about the language itself and Apalache and TLC. And then there's also some common like keywords you'll see. So the plugin, strongly recommend that. The TLA plus standard modules are automatically found when you include them in your spec. the list is here, and they we already saw one because we used it, which is sequences, and they just include some operators. So this is like the help operators that you were talking about. So yeah, so I mean, like, you can make libraries of operators that are like nice and reusable and import them like that. And there's a few that already exist. So like real numbers, randomization, integers, etc.
Is there a library, for instance, for well-known kind of modules that could be applicable to the kind of problems we deal with in Informal, like, you know, stake module or something like that?
Interesting. Not that I know of.
Okay.
Yeah.
I mean, the approach of TLA is not to reuse. The approach is copy-paste, as officially claimed by Leslie Lampard. Copy-paste and modify, simplify your spec to what you need. And basically, you always should keep your specification as small as possible, which means that reuse is like not actually encouraged. I mean, for standard modules, it's okay. But if you want to reuse a very powerful consensus, maybe you should copy it and simplify it to your needs. That's basically the idea. Yeah.
And I guess
that was my next question.
You already. And I guess if we have a module that is preferable to not try to model it, if we can just assume some properties and clearly state those. Right?
Yeah, definitely. Yeah.
So model as little as possible because you reduce the state transitions.
Yeah, so that's really the biggest challenge by far, is just keeping the state space small. Yeah, that's by far the hardest thing when you're writing models. And yeah, as you say, the best thing to do is if you can just like isolate some properties which you can rely on, so that you don't need to model how they work. That's the best way. Yeah.
Thanks.
Yeah, so that's the modules. The best forums are the the TLA channel in our Slack, and also this Google group TLA Plus. This is where the core team of TLA Plus also post, and they're actually very responsive in my experience. Then there's the issues page on the TLA Plus repo. So this is the repo that contains like the language parser itself, most of the discussion of the language direction, and also all the TLC model checker code. Whereas Apalache is at Apalache. Yeah. So that's that. Yeah, of course, the issues page here is also good. And then just some other keywords you'll probably see when you're reading about TLA is like, so Modelator, which is our model-based testing that we're developing at Informal, which will be the subject of another talk. And it's like, you can generate tests from a model. So you write a model and you specify behaviors that you want to see. And then via generating the executions, you can convert the executions into like, a sequence of steps, which you can feed into the real system and check that your real system is working. Sani, which is the parser, the canonical parser, which is used by TLC and Apalache. The Toolbox, so you'll see this a lot, and it's essentially like an old Eclipse toolbox, which is like an IDE for writing TLA+, but it's quite old, and to be honest, I wouldn't recommend it. Probably stick with VS Code. There's community modules, which are like just like the standard modules. So like, yeah, I don't know, like if there's too much useful stuff in here, maybe. This one could be used for some more like sequence operators, so like helper functions for lists, basically. Could be good.
How do we install or import a module?
So I would just copy and paste it, and just copy the file and use it. Yeah. You can do
it's like Node, right? When you just copy everything into your project.
Yeah. I mean, like, no one's writing specs that are like 15K lines, right? So it's fine. You can just copy and paste everything. Pascal, which is like a language which you write inside comments in TLA plus, and it translates to TLA plus, and it's like it was. I don't think it's still developed, but it was like someone created it as a language which was supposed to be easier to learn than TLA plus, and I would say it maybe is, but it's like much less expressive, and to be honest, like if you use it too much, you'll just get annoyed with the quirks. So I wouldn't recommend it, but you'll probably see the name thrown around. That's why I include it here. And then finally, like Specifying Systems, which is a book written by Leslie Lamport, which is about TLA plus and TLC, and there's definitely a lot of useful information, but much of it is outdated, I believe. Although that can be a good source because it's like very, like it's written very precisely. That's like the good thing, I would say. And yeah, there are many more tools. This is just a subset. So yeah, that's it for what I have.